emails pop up in the field. And nobody said, you know, here's a line of research on how humans evolved in terms of spatial hearing, what spatial hearing may have been important for in Paleolithic times. So it seems like there's an interesting line of research right there that I hope somebody may pursue. I'd like to do it someday. And then Scharf, of course, did a lot of classic studies in our field. And he laid out the idea that maybe one comparative advantage of spatial hearing is that it's a great warning system. It can sense what's going around you in all directions at a distance, and that would be important for detecting threats or recognizing opportunities. So we're trying to develop kind of a broader framework here for our specific spatial attention studies. And this is different from vision, you know. I mean, vision is great. I don't have anything against vision, but there are a lot of differences relative to spatial hearing that are important. And one is that it's very focused in space. You got the Lord of the Rings here, was it the Eye of Sauron, I think, or something like that. And that has an important implication as far as how spatial attention works in the visual system and why audition may have some differences. So I always tell my students, don't put lots of text on slides. And so I'm breaking that it's not really a rule. You can always, there's reasons for it. And I figured for us, it would be worthwhile just to articulate some of the differences in terms of cognitive level of function of spatial hearing, as well as the neural level, that may be important in thinking about, can auditory spatial attention tell us something about how attention works, beyond just saying that, yes, you can attend to things in the auditory modality too. And so one, which I'm going to focus on today, is the spatial range. It's panoramic. Whereas vision is quite limited. I calculate, if you think about this, the visual field on a sphere, it's about 1/6 of the sphere or so around your head and your body. But there are other things as well. Audition can detect sounds at many different distances, whereas there's usually a focal point or a focal plane for vision. Spatial acuity, of course, is much better in vision than in audition. But the differences across space are less in the auditory system. It's about, depending on how you measure, about 2 to 10 degrees using minimal audible angle, whereas vision, it's a couple orders of magnitude difference. The receptor input, the vision has a fovea, so you get color vision there, but you don't get it in other parts of the retina. We don't really have that in hearing. There's a blind spot. We don't have to worry about that. Probably because of the fovea, there are specialized motor systems for moving the eyes around to sample the world. And we don't need to do this sampling in audition. And if you're sampling over time, you want to retain that information over time. So there's visual short-term memory. Again, we don't necessarily need to have that feature. Of course, there is auditory short-term memory, but it's not necessary for sampling a scene. Vision fills, there's something to be seen everywhere, right? With auditory scenes, we can have very sparse scenes. We can have just one sound source, and other locations aren't really sending additional acoustic information. So that's an important difference. In vision, you can perceive lots of different objects within the scene. In audition, as we know from Zoom calls, if 2 people start talking at the same time, it's really hard to make sense of what they're saying. So all it takes is a couple objects in vision or a few, and then it's difficult to perceive what's going on. And then lastly, there's a long-standing literature on how, in terms of space, visual information tends to dominate auditory information. So we got the ventriloquism effect, for example. Posner had a pretty well-known paper that came out in 1976 on that topic. All right, so lots of cognitive reasons to think we want to study spatial attention in the auditory modality in and of itself, because it can inform us on how attention works. In terms of the brain, visual motor systems, frontal eye field, superior parietal cortex, superior colliculus, they overlap with attention systems. So that suggests also maybe some of these motor specializations may influence visual attention, and that may differ for auditory attention. Or auditory attention may use these visual motor systems for its own purposes. There are a few other things. There are visual kind of guided reaching pathways in the cortex. There may be some for speech, but it's not kind of at the level which you'd have with vision. Vision has a retinal reference frame right at the get-go of the receptor. In audition, we have a frequency coding initially at the receptor, so space has to be computed early on in the brainstem, but it still has to be computed. And then we have retinotopic mapping at many levels in the visual system. Auditory spatial coding is thought to be more of a population code as opposed to specific parts of the cortex reflecting specific parts of space. Okay, so these are many reasons. I think most of these topics here, really, I'd like to just go in and do a line of research on most of these. because I think it could be fruitful. But we're starting off with one of the most obvious, which is the spatial range is much greater in audition. So let's think about how this may work from a very general, kind of a generic cognitive framework for how attention may work. So we know that you can have supramodal attention control, especially with space. You can attend to particular parts of space, and different modalities at that location in space can all receive preferential processing. So there's supramodal attention exists. We want to consider, this is part of where I'm going with this line of research, is idiosyncrasies to controlling auditory attention relative to visual attention. Typically, we think about this as having some sort of top-down signal relative to goals. And so all the studies that I'm going to talk about today are endogenous attention tasks, where we tell the subject, I want you to attend to this location in space, and then they will, hopefully. So we're not going to talk about reflexive or exogenous attention today. So this top-down control signal can influence perceptual processing. Probably one of the most prominent frameworks is the bias competition framework, and maybe some sort of Bayesian way that could operate. But there's perceptual mechanisms that can be influenced by these top-down signals. Now, so I have similarities and differences here with our little schematic here, the motherboard for audition and vision. They both have chips, they both have wiring. They both compute things like spatial information, intensity coding, duration and time. But there's some differences. We have pitch, for example. That's one thing that we can focus on in the auditory system. We don't really have pitch and vision. You have color, shape, biological motion, things of that nature. So these differences at the perceptual coding level may perhaps demand differences in how attentional top-down coding, top-down bias works. And then just one last thing just to mention. So I made these arrows bidirectional because if we're thinking about attention as kind of an emergent phenomenon, these differences at the perceptual level may have implications for some of these higher level dimensions of control. All right. So previous studies of spatial attention, there are a lot of them that have focused on attending to a left ear versus the right ear using headphones, or having two speakers in front of you in the lab. So for today's purpose, I'm going to put those aside, which is the bulk of the literature. And the reason I'm putting it aside is we want to get a better sense of how spatial attention may be spread out over larger regions of space. So you want to sample more than two locations in space. When you do that, the literature gets far more sparse. So I found a paper by Ludwig Geisser from 1915, where he did a study on auditory spatial attention using an endogenous attention task. It was very complicated. I wanted to make a plot of some of his results. It was very complicated, a lot of tables. But he did the same sort of thing we've been doing now. Instruct attentions to attend to one part of space to get their, quote, best attention there, and then expect the sound to come from that. And how does that affect performance? And he found that as you would expect, people made fewer errors when stimuli were delivered at the attended location. There was a study by Rhodes a little over 30 years ago that it had some methodological issues that were criticized a fair amount later. But I think she was really onto something here, in that she found some of these reaction time attention gradients where you attended to one speaker and then presented stimuli either at that speaker or various distances away from the attended speaker. And that reaction times, in this case, vocal reaction times, got slower and slower as the stimulus was delivered farther and farther away from the attended location. And then it started to speed up once you got to the edges of the speaker array, which is something that I'll show you the similar sort of thing that we found later. And then if you have people attend within a 360-degree array of speakers around you, the reaction time slowed up to a certain point and then leveled off. So it was, even with methodological issues, it was a pretty good start, I think. Mondor and Auditory really went to town on spatial hearing in 1995. It's one of my favorite papers ever. And they also showed that you have these gradient effects where reaction times get longer and longer when stimuli delivered farther and farther away from where the person is focusing in space. And then lastly, Rorden and Driver had an experiment where they also found a similar sort of gradient, where at the attended location, you had best performance in terms of reaction time, and then slowing occurred farther and farther away from that location. So there were a number of methodological issues that were kind of worked out in the course of this line of research. And so we have a paradigm that was designed to try to come up with as clean a way as possible of trying to measure spatial attention over a wider range of locations. Most of these other studies, they focused on 30 degrees or 60 degrees away from an attended location. Taking into account this kind of ecological approach, we wanted to spread out the range to at least 180 degrees. And I'm going to show you some data later on where our range was 360 degrees around the subject. So in this example, we used either spatialized sounds using headphones or free field speakers. We got the same basic results, but we tell people, okay, here are 5 locations for sounds, looking down on top of the subject's head. We want you to attend to this location to your right side. And you're going to hear 2 types of sounds. They're both amplitude modulated white noise. One has a slow repetition rate of 25 hertz. It sounds kind of like somebody shuffling cards. And the other one is at 75 hertz, so it sounds like a buzz. So these are very easily distinguishable amplitude modulation rates. And most of the time, the sound comes from the standard location. But every once in a while, the sound will be presented at a different location. And regardless of where the location is, the subjects just make their non-spatial judgment of amplitude modulation rates. So we have the spatial dimension orthogonal to the non-spatial amplitude modulation dimension. So we could remove confounds that would relate to if you had them judging spatial locations and responding to that, as well as attending the spatial locations. The interpretation gets a little complicated. So I was expecting to find more or less linear gradient effects, but instead we found nonlinear gradients. So I'll give just one example here. If you're attending to the far left and the sound comes at that location at -90 degrees, people are fast. It slows down if the sound is a little bit to the right at the -45. It gets a little slower at midline, and then it starts to speed up in the contralateral hemispace. We see the same basic pattern, only more kind of not as much of a U shape when you attend to the right side. And that's a fairly consistent finding as well, that these gradients show a greater bowing when you attend to the left versus when you attend to the right. And if you attend at midline, these U-shaped functions are seen on both sides of midline. They're kind of scrunched together because, again, the range is just from -90 to +90. This is showing relative to the attended location, these U-shaped functions for each one of the 3 attended locations. And in control tasks, if we have people just divided attention tasks where the sounds are presented equally likely each one of these 5 locations, you don't see these gradients. It's more or less a flat line, or sometimes people are a little slower at the 45 degrees, but it's usually not a big difference. All right. So we did several experiments to investigate this phenomenon. One was to change the range of sound locations. So we made the range smaller, and we found that this inverted U shape also scrunched up together to fill the range that was allotted in terms of the spatial location. So we saw that when they're tending to the left side of space or when they're tending to midline. Interestingly, on the right side of space, we didn't see that compression effect. This was more of a kind of an allocentric or at least kind of an invariant coding here with the space. Even when the range was smaller, the reaction times are about the same when the range here was only 90 degrees as when the range was 180 degrees. So we've been seeing, we have a list of differences between left and right locations that we're going to test out with future studies. But it was kind of interesting that we saw this stretchiness of the attention gradient when you tend to the left or midline, but it didn't seem quite as stretchy when you tend to the right. In terms of top-down influences, so one way that you can classically test this is to give people a dual task, have them do 2 things at once. And so we had our participants in 2017 do the same spatial attention tasks I just described, only we gave them information to remember before they did their spatial attention trial. So we'd have them remember several words, for example, or we had them remember a spatial location. And we found that when we gave them a verbal load, we still got these gradients in terms of reaction time. Here they were just attending to midline. We didn't have enough time to have them attend to the left or to the right as well. And reaction time slowed down when the sound was presented away from the attended location, and then they sped up a little bit over here on the right, kept going slower and slower on the left. So we didn't see any effects of verbal load in 2 experiments. In contrast, when we had a spatial load, that did affect the shape of these gradients, and the gradients got more contracted, they got steeper. So you can see this best over here in the left hemispace, where with no load, you get this more gradual increase in reaction times away from the attended location at 0-degree midline. When you add on the spatial attention load, then the slope of this gradient gets a lot steeper. And notice it didn't affect overall reaction times at the attended location, right? So this is really how people responded to these shifts, these distractor locations, where we saw the effects of memory load. All right, so boy, this 20 minutes is going really fast. So I just wanted to let you know we've been doing some computational modeling of this to model kind of the top-down goal attention information as well as saliency information. And we're going to add in another part to this model based on O et al.'s framework that they proposed about 8 years ago that includes memory-driven memory-driven attention effects as well. All right, so we've been doing some recent studies expanding to 360 degrees, and we're focusing on attending to midline, but attending to midline at the front of you or behind you. As a first step, we did several tests to verify that people's abilities to perceive the sounds that we're presenting are comparable when they're presented in front of them versus in back. So we did some psychophysical studies here. We also did just plain old accuracy studies. The accuracy was pretty much the same all around. In the front, there were some front-back confusions in a few subjects, so the overall average here was a little lower than in back. This is when people are right off the street. So you give them a little bit of practice and then accuracies goes up even more. So there's no notable difference in their accuracies in terms of perceiving the sound's location. So when we had people do the spatial attention task, we started off by looking at the frontal hemispace versus the back hemispace, and also the left hemispace versus the right hemispace. And I'll give you just the bottom line information here, which is that these cueing effects, how much slower are they for these shift locations relative to the standard location? We see this in these block trials I've been describing where they attend to the same location for 6 minutes, or if we cue at every trial, we see the same basic cueing effects, only they're smaller when we cue on a trial by trial basis, but they're highly significant. This is the standard Posner effect. Many of you are familiar with that. So if we plot this cueing effect, the Cohen's d effect size, we did 5 experiments. 2 of them we did the front versus the back or left versus right. The cueing effects were much larger for the frontal hemispace when you're tending to the front or versus when you're tending to the back. We saw that when the range of sounds were in the front versus back hemispace, or if the range of sounds were on the left side versus the right side. The same basic effect was there. When we went to 360 degrees, we found the same thing, that these cueing effects, the benefits that you get for focusing on the attended location and the costs when the sounds show up somewhere else are much greater when you're tending to the front of space at midline versus the back of space. The overall effect sizes here were about 0.39 and 0.21. So it's almost twice as big of an effect in the front versus the back. All right, and this is showing some data from an experiment where we looked at the 360 degree range, but I'm gonna, because of time, I'm gonna just go past that pretty quick. And last, I just wanna introduce a study that we're just starting. We have 20 subjects in this, where we're measuring EEG while people do these tasks and compare attending to the front of space versus the back of space. So the experiments I just described, where those half a pies were kind of going across the frontal range from left to right versus the back hemispace left to right. We recorded EEG while they did that. And we used current density modeling methods that use biophysical assumptions about how currents in the brain are reflected by voltage on the scalp to define regions of interest that are known to be important for visual spatial attention, and a lot less is known about them in terms of auditory attention. The frontal eye fields and the interparietal sulcus here, the inferior frontal gyrus and temporal parietal junction, and then we also modeled currents in the auditory cortex. Now, I don't want to go through everything here, but just to kind of get the basics of, we found, as expected, spatial coding in auditory cortex that was greater for sounds contralateral to the auditory cortex we're measuring the currents in. In these dorsal attention systems, the frontal eye fields and the interparietal sulcus, we found spatial gradients as well early on, shortly after stimulus are presented, less than 100 milliseconds, that turned into these gradients centered on the attended location. And this is the key thing here. We found greater currents when the sounds are presented in front versus in back of the subject. We saw this in multiple locations within these regions of interest. We also saw that in the ventral attention network, similar sort of things. We saw it with oscillations in EEG power. So it's not just the current density, but specific oscillations important in attention control showed this effect. And we measured some interactions between regions of interest and also found differences for front versus back. We found no instance where there was a larger response when the sounds were behind the subject versus in front of the subject. And so we're playing with the idea that this may be an additive influence, that when sounds are presented in front, they overlap with vision, the space that can also be processed by the visual system. And that may be showing this influence on the behavioral effects that we saw earlier, as well as some of these current effects that we're measuring in the brain. So just to wrap it all together, so I think in addition to, you talk with the visual attention people and they'll pat you on the head and say, okay, great, attention works in the auditory modality. That's nice. But I think there's more to it than that. As I explained, there are idiosyncrasies or these differences between vision and audition that I think have core implications for how attention works. We found these nonlinear endogenous attention gradients oftentimes have this nonlinear shape. And we're starting to move into the brain to try and relate how brain processing relates to behavior and differences for front versus back hemispace. So for that, I just want to acknowledge my collaborators here, my doctoral student, Andra Bodnar, Brent and Jael were involved in some of the modeling studies I didn't talk about. And of course, we're grateful for funding from the NSF and NIH. And I'd be glad to take any questions. Thank you very much.
Okay, and thank you, Dr. Golob. We have about 5 minutes for questions. We have one from John Newhoff, who says, fascinating work. Do you have any general thoughts on how auditory motion and distance interface with your results?
Oh boy, yes. I've been wanting to get into auditory motion for several years. And it's just been a matter of priorities and also funding. But we're going to move in that direction, yes, as far as thinking about how auditory motion and some of kind of maybe some of these more exogenous effects of a sound that starts to move, how that may relate to some of these attention frameworks that we've been developing. We're also actually, Tim, working on representational momentum as well as kind of another project. And so I'd like to at some point kind of blend these two lines of research together. But yes, I'm very interested in auditory motion perception.
Oh, yes, we'll definitely have to speak about that later on. I think that could be quite interesting. Mike Russell also asked, on a related note, how do your results relate to sound location that vary in distance and elevation/altitude?
Yes, excellent. You're laying out all these things I really want to do. The distance one has been on the agenda as well for a long time. We haven't done anything with it, and I think it's really important to do so, because really what audition has to work with in terms of space is a filled sphere centered on the head. So distance is something that also, of course, it's challenging to, distance perception is pretty variable in audition. But it's another thing that I would just love to work on in the future. We haven't done anything with it, actually. And also thinking about looming versus receiving stimuli, in John's work, as far as kind of, how that may relate to evolutionary considerations and threats and warnings. Yeah, there's so much to do with this.
Okay, excellent. We have a question from Peter Fordresher. He says, you mentioned differences in how many objects can be perceived in audition versus vision. Is this reducible to differences in acuity across domains? Also interested in how long-term experience could play a role given data on auditory spatial attention in orchestra conductors.
Okay. Yeah, as far as the long-term memory aspect, that's why I'd like to, we started to get at that. As far as I mentioned in our model, we want to introduce the selection history is what O et al. Called it. I think of it more in terms of just memory. That's a simple, less jargony way of thinking about it. But we know that stimuli that aren't necessarily related to a goal or that salient can attract attention nonetheless. Think back to Murray's dichotic listening studies in cherries, where people will notice their names, for example. So I'd like to work on that. We've been looking in terms of statistical learning. and how these gradients that I've been showing in terms of reaction time are very sensitive to the probability of the stimulus shifts. And so if you make shifts a little more likely, I mentioned earlier that on 4% of the trials, any one of those 4 shift locations are used. If you move it up to 12%, basically the reaction time function flattens out. Even though over half of the trials are still being presented at that standard location, so you'd think that there would be utility in attending to that in terms of reaction time, but it looks like that goes away pretty quickly. As far as longer term memories, we haven't done anything with that, but I think that's another, potentially really fruitful line of research. And I'm sorry, what was the first part of the question?
How many objects can be perceived in audition versus vision? Is this reducible to differences in acuity across domains?
Yeah. I'm not sure. In some ways, I guess it would have to be, as far as defining distinct objects. That's limited by how well can you define the object in terms of acuity. But I think he's probably getting at a deeper question, and I'm not sure about that. I think it's an empirical question, right? You'd think, for example, if there are individual differences in acuity, how would that map out into some of these attention effects? And maybe that may be one approach to the question.
Okay, I will ask one question. When you were showing the data, showing the differences between left and right attention, I was kind of struck by how some of that paralleled the data on hemifield neglect. So I was wondering how you might see your data on audition attention relating to hemifield neglect and potential differences between, say, left and right parietal and processing locations.
Right. Yeah. I think that's probably relevant. And my student Andor, as part of the EEG study, we have a lot of data and a lot of ways of analyzing it. And he's focusing on, for his work, the right temporoparietal junction, which is an area that's probably the most common area to sustain damage that leads to neglect symptoms. So we're going to get at it that way in healthy brains. And then I haven't worked with neglect patients yet. That's another thing. I'd have a long list of things I'd like to do. That could be another approach to all this, especially because these paradigms that I showed you, we've replicated the results many, many times. And so we know kind of, as far as the paradigm goes, what to expect. I should have mentioned earlier, we ran healthy older people on this task as well. The paper came out in 2019. And as far as the attention gradient part that I showed you today, it was basically the same results in healthy older subjects. They're age 65 to 75, I believe. So at least in healthy aging, you get pretty much the same thing.
Oh, very interesting. We need to move on to our next session. So we thank you for your speech, and I'm sure if people have questions, they'll be putting them up in the chat and emailing you on them.
Okay, excellent. Appreciate that. Thank you very much.
And thank you.